Hey guys, this is Miss Weaver, and I am doing a quick review over section 8.1. There were three main concepts that you should have seen in the interactive assignment for 8.1. The first one is being able to define what a sampling distribution is and also describe it. Then also you should be able to identify the mean and standard error of a sampling distribution. And finally, we should be able to understand and use the central limit theorem. So our first question is, what is a sampling distribution? And you defined this on the first page, I guess the second page of your guided notes for chapter 8. At the bottom, what is a sampling distribution of a statistic, and what is the sampling distribution of the sample mean, x bar. But real quick, just how we would define or describe what this is it's a probability distribution and if you remember when we talked about probability distributions in chapter 6 notes, when we first started describing or defining a discrete probability distribution, and then in chapter 7 a continuous probability distribution. Remember that a probability distribution just describes the possible values that can actually happen, and then the probability for each of those values. And with a sampling distribution, it's a continuous probability distribution that just gives all possible values for a statistic computed from a specific sample size based on so of course remember we say n equals whatever we choose. N is our sample size, and so this probability or this sampling distribution is, we can have sampling distributions for the sample mean, we can have sampling distributions for the sample proportion, and even for the sample standard deviation. However, we're only going to focus on the sampling distribution for the sample mean. And so, and our sampling distribution for the sample mean, which is x bar, is simply the probability distribution of all possible values for x bar coming from samples of size n, whatever that one particular sample size is. And these sampling distributions change as the sample size changes. All right, so one thing that we talked about back in chapter 3 was how to describe a distribution. Not necessarily a sampling distribution, but just how to describe and we had three things. Well, technically there's four, but outliers when we're talking about sampling distributions we don't worry about. And I usually say don't forget your socks. So, no K, but don't forget your socks. The first S is for shape. And remember we talked about several different shapes. We talked about a uniform distribution. We talked about a normal distribution, and we talked about skewed distributions. The O, which we don't really focus on in Chapter 8, is for any outliers. When we're describing a data set, we definitely want to identify any outliers that we might have. And then the C is for the center. So typically this is going to be the mean, but it could also be the median. Oops. And then finally, we have spread. So this is going to be our standard deviation, or possibly interquartile range. Of course, with what we're doing in this chapter is we are definitely looking at the mean and the standard deviation. But that's our way to describe any distribution or any data set. Hopefully, as you were going through the guided notes and the interactive assignment for 8.1, you realize that there's a lot of similarities with what we were doing in Chapter 7 with the normal distribution and the normal CDF. And in fact, there definitely is. From what we were doing in Chapter 7, we were using something, I'm going to pull up a picture here. We were using something like the IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. And that looked something like that right there. And we could say, well, if I wanted to find a specific value or the chance of being above, below, or between, then I would say, well, if I wanted to know what's the probability that somebody has an IQ above maybe 120, I'm just kind of estimating there, then I would find the area under the curve here using my normal CDF. And we're going to do similar things with that, but there is a difference, there's a change now, because what we're doing, instead of looking at the entire population, is we're now looking at what if I took lots and lots of samples. And so, for example, let me pull up another picture really quick. If I took a lot of samples, one of those samples coming from this population might look like this right here. And so here's our data distribution of one sample of size 100, n equals 100. You can see right here. And this is very near a perfect sample, if ever could be one. Our sample mean is still 100, and our sample standard deviation is actually still 15, just like our population was. And you can see that this looks very symmetric. It's not perfect. We have, this is a bit lower than here, but it's still very nicely bell-shaped and all of that. So what happens if I do this? I take samples like this, and I do that over and over and over again. What I end up with is lots of little sample means, and all of those sample means fall into place and end up creating another distribution. So we had the population distribution. We had a distribution of a sample. So this is my sample data, and I can describe it. It's also approximately normal with a mean of 100 and a standard deviation of 15. But then we have the distribution of all of those sample means. So what if I take and I find $1,000 sample means. I find X bar for 1,000 different samples, just randomly selecting people, since these are IQ scores, from that population. That's going to look differently because when I average or take the mean of multiple values, so again, X bar with n equals 100, even if I just take two people's IQ scores and I average them, then, if I end up with one person who's here and another person who's here, then their average might be, somewhere in, obviously add them together, divided by 2, it's going to be right between those two. And so my average isn't going to be quite as extreme as my larger value or my smaller value. If I add more and more people, then that average is going to end up, what's going to happen is that average is going to get closer and closer and closer to where the population mean would be. So let's look at this if I do 1,000 samples. Okay, so we just saw a sample that was nearly perfect if a sample could be perfect. It came from the distribution with the exact same sample mean as a population mean and the same sample standard deviation as a population standard deviation. I want to show you a couple of more that are just a little bit different so we can see that these sample means, of course, samples vary. That should be something that we know and remember from the beginning of class. This sample here has a mean of 103 and a standard deviation of 14.2. So a little less spread out and a much higher mean, relatively speaking. You may think that 3 points isn't that high, but remember, this is a sample of 100 individuals. And so our our sample mean, for it to go up 3 points, that means that there's a lot going on with these higher values, and our lower values aren't as low. Now, if we also take a look at another one here, just for comparison's sake, this one has a sample. Whoop, I picked the wrong one. Let me try again. 2. There we go. This one has a sample mean of 96.1 and a standard deviation of 13.5. And as you can see, so remember, sample means where the center is. These are lined up. The 100s are about lined up here. Trying to get them pretty much in the same spot. The blue triangle is to the right on the top graph, to the left on the bottom graph of that red semicircle, which is the population mean of 100. And so we can see that there's 103 versus 96.1. So it's like 7 points difference. And again, these are means of 100 different IQ scores. So to be moved that drastically for that many people, there had to be a really huge difference in these values. All right, and then what do these end up looking like? So what is this sampling distribution of the sample mean? Well, I've got one more image or one more file to bring in, and it actually shows just the graph of these sample means for a little over 1,000 simulations of sample size n equals 100. In fact, 1,029 samples. And the reason for that is because I was looking for, kind of kept doing those random samples so that I could get these two examples above, just so you could see. And so, for example, now this scale is much wider. Notice that, this is from 100 to 102 is quite a big space. So this scale does not match up with this scale or this scale. But what does match up is I took this picture, a screenshot, at the exact same time that I got that second sample. And there's that 96.1. It's way down here in the tail. That's an extremely unusual sample mean to get if we're taking samples of size 100. And then our 103, it's not marked on this graph, but that would be right down here. Right there would be 103. And so both of these samples, even though they don't look that drastic, both of these samples that we have on top in the orange graphs are really extreme values for our sampling distribution. But these sampling distributions are all the different x-bar values for multiple samples of size 100. So hopefully that helps you understand what a sampling distribution is.